Hello everyone, I am Yunwen Zhou from Google AR. I'm happy to present the work Learned Molecular Depth Priors in Visual-Inertial Initialization. Visual-Inertial odometry is an important underlying technology that enables AR experiences. It estimates a device's real-time 6-degree of freedom pulse in an unknown environment. In this way, the AR content can be rendered to lay over the real-world scenarios, as shown in the AR core example here. The method we propose is shaped in AR code that helps the user to start faster and more reliable AR experiences. It is also highlighted in Google I/O 2022. Please scan the QR code to check out. Initializing VIO fast and robust is critical for the user to enable immersive AR experiences as soon as possible. However, it is challenging in the wild. A typical solution for initialization is to form a visual-inertial boundary adjustment problem with a small number of keyframes. The ideal case for initialization includes high visual parallax, rich texture scene, and enough motions. But it is rare in the real case. Low parallax, textured scenes, and insufficient motions trouble the initialization. For example here, small motion results in small baselines that can lead towards big uncertainty for landmark triangulation to solve the initialization problem. So we propose using the power of a light-weighted molecular depth model to address the problem. The model is trained on scale and shift invariant loss so that it yields up to scale and shift inverse steps. To recover the metric inverse steps, we should apply scale and shift parameters. The learned depth priors can largely help reducing the uncertainty of the landmarks for initialization. Here we present the overall system diagram. First of all, we run the inference on images to get up to scale and shift inverse depth prediction. Secondly, we form a visual-inertial boundary adjustment problem to solve for the initial states for VIO. For each triangulated landmark, we associate it with the monodepth at its observed keyframes. Additionally, we introduce scale and shift terms to constrain all observed landmarks at the same keyframe during the optimization. Finally, we pass the resulting initial states, including keyframe poses, IMU biases, and velocities to the VIO filter to start with. Here we present qualitative results of our VIO initialization. The first row shows sequential images used for VIO initialization as keyframes, and the feature tracks are those used for triangulating landmarks, which are associated with monodepth measurements. Some monodepth measurements can be erroneous and inconsistent across keyframes, so we reject those. The second row is the up to scale and shift monodepth, and we can see the off the metric scale and inconsistent row network predictions. The third row is the metric depth of recovered from monodepth by optimized scale and shift parameters. We can see obvious coarse frame depth consistency versus the row above. We evaluate the performance of our proposed initialization method on public UROC dataset. We ran two sets of the experiments. First of all, we run exhaustively create initialization events on the dataset and evaluate the initialized states. The second one is that we evaluated the VIO performance built on top of different initialization methods. We see significant improvements across all matrices on both evaluations. Thank you. Please scan the QR code of the project page for more details.